Okay, example 5 says find y prime the derivative if sine of x plus y equals y squared cosine of x. And y prime is what they're using. When we do implicit differentiation, I prefer dy over dx. So I'm going to be using dy over dx in my work instead of y prime. If I write y prime, then it's kind of confusing in the work. So dy dx is a much different looking thing, so it kind of stands out. Okay, so if we take a look at our terms that we have going on here, term 1 is sine of x plus y, and term 2 is y squared cosine of x. And terms are separated by pluses and minuses and equal signs, so you see an equal sign separates those two terms. And again, before I start differentiating, my first goal here is to establish what kinds of functions am I dealing with, what types of differentiation rules do I have to use to differentiate. And this thinking process is the step that some of you are leaving out. You see a problem, you start doing it. Before you think through it, before you can decide technique, before you do anything, you see something, you just go with it, and that's where some of you are getting into trouble. So, looking at the blue highlight here, sine of x plus y, what I'm looking at is a sine function. So I'm thinking about this derivative of sine as cosine. Okay? And what I see is an argument not of x, but of x plus y, so I'm looking at a composite function, so the chain rule comes to mind also. So, in my mind, before I start differentiating that piece, I know it's a sine function, and I'm going to have to use the chain rule to differentiate. Alright? So if I'm going to differentiate sine, the derivative of sine is cosine. And when I do differentiate any trig function and I do its derivative is, again, sine's derivative is cosine, the argument is going to stay the same. Okay, so cosine of x plus y is the derivative of sine of x plus y up front. Just applying the derivative of sine, nothing else. Now again, we're not differentiating sine of x, we're differentiating sine of an expression that involves x. So now I have cosine of the same expression. Now I have to differentiate the expression x plus y. It's going to multiply by this whole expression here. The derivative of x is 1, and I'm differentiating x, so it's just derivative is 1, the end. And I have to differentiate y, its derivative is also 1, but I have to put a dy dx attached to that because that's an expression involving y. When you differentiate, you put a dy dx. What's in this bracket is not being multiplied by x plus y, it's being multiplied by cosine of x plus y. So this is being multiplied by this. These things can't interact. What the x plus y and this cannot interact with each other. So that's another thing you have to understand with some of this stuff. When you have any kind of function, a square root function, a parenthesis to a power, any trig function of stuff, the argument of that function is not going to interact with other stuff outside that function. All right, so that's the derivative of the blue highlight is that, and that's all you can do to that. Then of course we have our equals sign. And next we have this second function over here, y squared cosine of x. So again, what I have to do is look at structure of the function to establish, or structure of the term there to determine what kinds of things are going on here. Y squared is a power function of y, cosine of x is a cosine function of x. These two objects are being multiplied together. That brings to mind the product rule of differentiation. Each individual piece by themselves, y squared is really simple. It's a power rule. Cosine of x is just the cosine rule. And it's cosine of x. It's not cosine of weird stuff. It's just basic cosine of x. So it's a product of functions. Function 1 is y squared. Function 2 is cosine of x. The product rule is 1 d2 plus 2 d1. And as was discussed on Thursday, d2 and d1 is when I'm differentiating. That's when I worry about, do I need a dy dx or not. When I write down 1, I don't care about dy dx, I just write it down. When I write down 2, I don't care about dy dx, I just write it down. So, looking at this, let me use some different colors here. Let's go with, I'll do the reds as the 1 and 2, and the greens as the d1, the d2 and d1. So, if I do 1, that's y2, y squared. Okay? I just write it down. I don't care if it's x, y, z, w, dog, doesn't matter what it is, just write it down. That's all 1 is. d2 means I take function 2, which is cosine of x, and I differentiate it. The derivative of cosine of x is negative sine of x. What I differentiated is an expression involving x, so nothing extra necessary. Anytime you're differentiating x, you just get the derivative as you always have up to this point. Then there's a plus sign. There's always a plus sign. And then when I do 2, 2 is function 2 exactly as it's written, which is cosine of x. Nothing happens to it, nothing weird, just write it down. And when I do d1, the the derivative of y squared is 2y, and again, this is a derivative. I differentiated this expression. That's a y expression. I got this derivative of 2y by the power rule, dy over dx, because I differentiated an expression involving y. Okay, so again, that dy dx shows up. This time it showed up in an x term. This time it didn't show up in a y term. Again, it doesn't matter about what this red thing is. It matters about what you're differentiating to establish should I put a dy dx on it or not. Okay, it's not just some random thing that, oh, I haven't put a dy dx in a while, let's just put one on there. It's not, that's not how it works. There's an actual reason why you're putting it there. Alright, so that's job 1, is differentiate. At this point I've done my calculus. From this point forward it's an Algebra 1 problem. Kind of an ugly Algebra 1 problem, but it's an Algebra 1 problem. We want to get dy dx equals, so notice I've got a dy dx here and here, and I want to get that thing equals everything else. So at this point it's just a matter of simplify the equation, isolate everything that contains dy dx, solve for it that way. So what I have here is cosine of x plus y times this binomial. This multiplies by this and by that to get rid of the brackets. Cosine of x plus y times 1 makes cosine of x plus y. Cosine of x plus y times 1 dy dx makes cosine of x plus y dy dx. Y squared times negative sine of x makes negative y squared sine of x. Cosine of x times 2y dy dx makes 2y cosine of x dy dx. Okay, as a general rule for me, when I'm working, and again, you got to come up with your own idea of how you write stuff so you know how to interpret things you're writing down. If I'm taking cosine of more than one thing, I use parentheses. If I'm doing sine or cosine of one thing, I don't use parentheses. So if I don't see parentheses, I'm expecting it's sine of x, that's it. This is cosine of x and that's it. If I wanted that dy dx inside of that, I put parentheses around the whole thing, but it's not supposed to be that way. Cosine of x is here, the dy dx is separate from it. So if I'm doing cosine of a bunch of stuff, I put parentheses. If I'm doing sine or cosine of just one thing, I just write it down. That's my personal preference. If you prefer to put a parentheses around every argument you've ever seen, that's fine too, just as long as you have the ability to look at your work and interpret what is what within each term. This is a term. This is a term. This is a term. This is a term. Again, always term separation is separated by pluses and minuses. Okay, cosine parentheses x plus y. There is a plus sign there, but that whole thing, this belongs to the cosine functions. Cosine of all that is a term. Cosine of all this times dy dx. These are being multiplied, so all that's a term. Y squared and sine of x are being multiplied in term. 2y is being multiplied by cosine is being multiplied by dy dx is a term. That's another thing I've noticed in your work. Some of you, when you get to the algebra step there, you're taking pieces of terms away. Like you'll take this sine of x and just move it over, leave the y squared there or something like that. And I don't know, it just seems weird to me because I can see so clearly where each of the terms is. Some of you aren't seeing that as clearly, so I'm just trying to make sure that we understand all that. So looking at the underlying terms, these two guys both have a dy dx, these two guys don't, so we got to move things around. I like my dy dx on the left hand side, that's what I'm going to do. So I'm going to keep this where it's at, and I'm going to keep this where it's at. I'm going to move the other two guys. So I've got to move a 2y cosine of x dy dx over to the left. I'm leaving a plus cosine of x plus y dy dx over on the left. The equal sign is just going to stay right where it's at. I'm keeping my negative y squared sine of x right where it's at. And I'm moving a cosine of x plus y over to the right. Just using basic algebra, if you move an entire term, you change its sign. This is positive, moves over as a negative. This is positive, moves over as a negative. The stuff in red stayed where it was, so this stayed positive, this stayed negative, because they stayed where they were. This is a common place you're going to get to every time you do these problems. Okay? The first day we did implicit differentiation, we had just a dy dx thing, and we just divided when it was all ready to go. Most of your problems, you're going to get multiple dy dx terms. So what you're going to do is you're going to factor that out, parentheses, this plus this. That's the uncommon pieces of these two things, times dy dx, the common piece, equals, and then you just rewrite this exactly as it is. So if you have a clone function on your paper, you do that, clone it. Nothing happens to that side. If you don't, you got to rewrite it. All right? And again, that step happens almost every time in these problems. You get a bunch of things, dy dx equals a bunch of things. You write down the bunch of things, and one parentheses times the dy dx equals the same bunch of things. And then you take, to get dy dx, I've got this divided by that. And just to look at a more basic structure that you're more familiar with. 2x equals 8. What am I supposed to divide by? 2, because that's being multiplied by x. All this stuff times dy dx. I want to get dy dx equals, that's my goal. So just like I want to get x equals here, I've got to divide by 2. I want it to get dy dx, I've got to divide by that stuff. So I'm going to get this stuff on top, negative y squared sine of x minus cosine of x plus y on top, divided by the stuff being multiplied by dy dx, which is negative 2y cosine of x plus cosine of x plus y. That's exactly the right answer. I do have the option at this step up here where I move things around. I could have moved the dy dx stuff over to the right and all the other stuff to the left. The effect that would have had, if you recall from solving advanced abstract equations, is all the signs would be different. You do still get the same answer, y squared sine of x plus cosine of x plus y over positive 2y cosine of x minus cosine of x plus y. Had you gone the other direction. So if you're checking your answer in the back of the book or in the solutions manual, you got this answer, they got that answer. Just know to compare them that way. All the same pieces in all the same places, every term is an opposite sign. That's the exact same answer. Again, it has to do with where did you move things.
Yeah, I noticed that.
And again, the book's a little weird about where they move things. I personally like to move dy dx left every time. They jump around. They do it more to the right, sometimes left, sometimes. They don't have any rhyme or reason to it. They don't have a system. I have a system, always to the left. So anyway, but again, that's the right answer. You may or may not be able to reduce. Be careful if you're reducing trig functions that arguments are the same. This sine of x and this cosine of x are both of x, cosine of x plus y. Now these are both cosine of x plus y, but they're pieces. They're not the entire top or bottom, so you can't divide by them. You might be tempted to try that, but you can't do that. So, kind of remember your algebra rules as you go, is the moral of the story, I guess.